Assalamualaikum warahmatullahi wabarakatuh. Let's look overall of chapter 9. So you will find the idea of momentum that we are going to cover to be in number 1, the generic idea what is momentum. So you're going to see as well at this version where momentum is equivalent to impulse as well. And the types of analysis will be in 1 dimension and 2 dimension. For 9.6, it will be concept. Center of mass will be a concept, which will be later in depth in chapter number 10. So here we are, the examples. Alright, looking at our textbook, chapter 9. So these are the required subtopic that we are going to see. 9.1 up to 9.6. Alright. So let us start with the idea of linear momentum. Perhaps it will be very focused to straight away looking at what is a momentum. So what is a momentum? The clear-cut definition of it is the product of mass and the velocity. So mass and velocity, hence it's a vector quantity. Okay, it's a vector quantity. Right, so since it's a vector quantity, negative and positive really brings an input not to be neglected. Alright, now in this overall topic, the very beginning, we are not going to see first the idea of components, but when later we look into the idea of 2 dimension, okay, so you are going to see this idea x and y comes into picture. How about z? We will find that our level is up to 2 dimension. Right, now, so let's have a look at the concept. Okay, this concept regarding what is the difference when you look at kinetic energy and momentum. Now, first and foremost, just now we did mention that momentum is a vector, whereas energy kinetic here is a scalar. So it's just purely a value. Right. Now, when we go deeper into the idea of Newton's second law, in fact, we have seen this in the previous topic when we deal with work, okay? And when we deal with work energy theorem, in fact, to be precise, okay? That's one way of looking at it, whereby the effect of doing work is you find there is a displacement. However, another way to look at it as well, to relate with the time, at time, we find that the change of the momentum, now mark my word, the terms change in the momentum is actually equivalent to the product of what we call as impulse. So what is impulse here? Impulse is force time delta T. Alright, so let's leave this for a while, but as something to take away, just remember that change in the momentum here, mass time delta V, is equivalent as well to the product of force time delta T time. Right, let's have a look at this quick quiz 9.1 here. So it says here you have 2 objects. They have equal kinetic energy, which, for example, we says that the expression is half mass and v squared. Okay. While momentum is mass times v. So, in the case that if we are to compare their momentum, how would it looks like? Now, so earlier half mv squared is kinetic energy. So I am now making it becomes mv squared divided by m. So as simplified, it's the same thing. Now, product of mass times v is equivalent to momentum. So you find that kinetic energy is equivalent to 1/2, okay, times momentum squared over the mass. So you find as well here that the kinetic energy and momentum somehow related to this version. Means that in simpler version as portrayed here, that kinetic energy is half over 2 momentum squared over m. So you can't really directly see how they are correlate with one another. You find that we have mass here as well. So the simplest way, okay, so I'm saying that this expression not enough to tell us any information yet, okay. But let's look at, if let's say we have mass equivalent to 1 v, velocity is 2, and a second object, let's do it the other way around, mass is 2, v is now 1. They have the same momentum, am I right? However, when you do substitution into the kinetic energy, they have difference in value. So the best answer should be we do not have enough information to tell which one is which. Okay, should they have bigger or should it have lesser? So that's somehow. But overall, I pick this quick quiz because I like you to see this expression that you can at any time, so long understand the concept that momentum is mass times velocity, you can do the manipulation on the equation. Now, so we have seen earlier that momentum or linear momentum is product mass and velocity. So we are going to go a bit harder, not a bit harder, one step ahead. So how? We are going to go over what we call as conservation of momentum. Conservation of momentum. In isolated system, whereby isolated trying to say that no external forces, for instance, friction, okay, you find that the system would have a total momentum equivalent at any situation. For instance, that it's trying to say is the initial total momentum should be equivalent to the final total momentum. Alright? And amongst way technique of writing, for instance, reflecting to this version is this expression. However, it's also correct to put it in this version that delta momentum is equivalent to 0. And notes that this is total momentum minus total momentum. Alright. So again, the terms isolated indicates that no external forces, in which we seen earlier, no friction. And in fact, we seen earlier as well that change in the energy of the system would be 0. AKA, energy final minus energy initial equivalent to 0, or delta K plus delta U equivalent to 0. So that's the idea that it's trying to portray. So if the question state conservation of momentum, so you're just supposed to say that when the total momentum of the system, of a system, does not change, stays constant, pick your own words, provided that these two are here, provided, tambah lagi satu lagi it's an isolated system. It's an isolated system. So once again, so total momentum of a system stays constant in an isolated system. Alright, with the idea of momentum supposed to be conserved, we're going to look at example 9.1 in the case of an archer. So the situation proposed is that we have 60 kilogram archer originally at rest and there is no friction. There's no friction. So terms originally at rest is trying to say that the initial velocity is 0. Initial velocity is 0. All of a sudden, what happened next is he fired the arrows horizontally at this speed. So you are about to see that there is changes in the velocity from 0 and goes to 85. Changes in the velocity here, somehow you can relate to the concept of momentum. Okay, and with that, when it start asking you what will be the final velocity after the archer move across the ice, it gets you a little bit confused because you already seen that this is velocity. But what you really need to understand that, as in the picture here, it try to portray that the total momentum initially for both is actually equivalent to 0. But right after that, he released the arrow. By releasing the arrow or firing the arrow, now the arrow now have velocity. Since the arrow have the velocity, you will find that he and the bow will also acquire velocity. And that is the velocity of asking questions. All right, asking questions. So now have a look at how the solution, with the idea that the momentum supposed to be conserved, look how they substitute the idea of the initial momentum, that originally there's nothing happening, no movement at all. And therefore, for both arrows and the archer will have a momentum equivalent to 0, right? However, right after that, which is the final, in the case that he released it, you will find that the arrow just now acquiring 85 in the direction of x direction. And that makes sense that you have to modify the expression of v in the I direction as well, or in the x direction as well. So you find that somehow when you simplify, you will arrive that the expression comes with a negative value for the archer. And you find overall, as you do the simplification, the answer is in the negative direction, showing that he will be moving backward as if being rebound. Okay, and this is the answer. Do you need to portray the answer in the I direction? You can choose to follow the exact as in the figure, okay, exactly as shown here, or you can omit this. Okay, why? Because you already seen that the whole process from the beginning occurring in the x direction. So you do not need to consider the y direction. So only without the I would do correctly as well. Alright, 9.3 analysis model. This time around, we are going to see that the case is non-isolated. Since it's non-isolated, we are going to see the effect when we have an external force. Now, this is especially when you find the question or the situation make contact. Ada sentuhan dengan something else, make contact. Alright. In this case, before we proceed, you're going to see the idea of impulse, which is F time delta T, and also the correlation with momentum. So how do we relate them? That the change in the momentum is equivalent to the impulse. Okay, which is impulse is F time delta T. Now, you observe something here. The F here is a quantity which is a value of force, right? So, how is it possible? Whereas in a situation involving contact, we find that we might have varied value of force. For instance, the graph A here, we find the graph is a bell shape. However, further study shows that when the collision, when the contact, okay, for instance, try to imagine you holding a bat, pegang bat, pukul bola, hit a ball, alright? Now, that force, okay, is actually a curve force. Okay, the force somehow varied with time because after that, the ball just leave you. Okay, it comes to you, make full contact, and then goes away. Now, in that sense, when time is very small, a very, very short time, they discover something that the area under the curve, which equivalent to the product of impulse, okay, equivalent to the product of impulse, is as equal to the product of having it half of the maximum, half, and force average, okay, and the whole product of the area here is the same, But of course here you must consider the situation having a very small. So maknanya macam pelanggaran tu happen very, very fast. Okay, very, very fast now. Now, so in that case, therefore they realize that, oh, okay, now we can make use of this equation that force is supposed to be a constant value, So then again, to wrap everything again, so we find that this impulse momentum theorems tells you that the value of change in the momentum, okay, change in momentum is equivalent to the product of impulse, okay, of when net force acting on any object or any particles in this case. Alright, coming to this expression, okay, why is it that mv is not equivalent to m force times delta t? Because of this one, okay, it's not this, okay. So this is just momentum. It must come with the change in the momentum because it's also present as mv final minus mu. Okay, the change is really without this delta, it means something else. Okay, so extra careful on the expression if it's without the change. It's portraying different situation. Alright, uh, an example of this scenario is this figure 9.4 where we have a dummy brought to rest because of a collision. So ni dummy. Alright, so we find the scenario. It's very helpful that you have the airbag because it's just increasing the time. You can see this in this version whereby when you increase the time, hence you decrease the force. And this is what we want when it involves human life in accidents. Alright. On the other hand, looking at the other opposite side, having collision with the smallest times will increase the amount of force. And we don't want this. So this average force become reduced when longer time interval. And that goes the same for us as well when we jump. So when we jump, we bend our knees. So that actually increasing or longer time interval. Now, let us look at the example where we will apply the expression impulse momentum theorem, which is example 9.3. Okay, remember that we are going to apply impulse momentum theorem. So, the situation in this example is we are going to see this car that travels negative 50 meter per second hit the wall and then rebound. Now, we are going to find the value of the force, okay, and then compare what if the final velocity is 0, okay. would it make any difference or not? Because this will discuss the shape of the front boot, okay, the design itself. Now let us look at the question. So in this particular car crash, there was this car, 1500. It collide with a wall as shown. So the initial velocity is negative 15 and the final velocity is 2.6 meter per second respectively. So they already include the direction. So we have to consider that because this is momentum. Now, if the whole collision lasted for 0.15 seconds, calculate the impulse, meaning to say that either you are to use F time delta T, yeah, however you don't have F, okay, let's just leave it for a while, and also the force, okay, the average force. Okay. Now, let's now look at the solution. We are aware that we don't have force time delta T. But at the same time, we do realize that impulse mathematically is also equivalent to the product of change in the momentum. Since we do have the mass and we do have the velocities for initial and final, therefore we are going to use that quantities. And making use of that quantity, look again that V initial is negative, right? Meaning to say that you are to include everything in the form of belonging to the directions, okay, and arriving with this answer. Now, another common question asked by my students is, can I skip the direction? So in this case, since linearly it occurred in only x direction, hence in the direction of I had, that it's safe enough to just jot down in what you have learned in high school, meaning to say 2.6 just plus 15 and that's it, portraying the final answer. It's okay. It's okay. Eventually, most importantly, you understand that the whole thing occurs in the X or Y direction. Hence, you can straight away process the info. Boleh terus sahaja. Okay. Now, when you do the calculation of force, take out the impulse, divide with the time, arriving with this one, meaning to say it's also correct to just jot down 1.76 to the power of 5 Newton. Okay. Now, I'd like you to make a comparison whereby what if the final value is now a zero value, yet we remain the same interval time. We find that from the calculation, okay, this is the value of the impulse, which is a bit smaller, and therefore resulting the amount of force, which is a bit smaller, So, in conclusion, we want the force to be much smaller, and that make sense, okay? Why the design of the front boot is supposed to be crumple. Now, we are on 9.3 where we are going to see that what if the system is not isolated, meaning to say there is an external force acting in the system. Might be friction, might be somebody pushing on one object, all right? So what happens and what are our tools? Now, our first tool is something that you have seen earlier with the idea that momentum is mass time velocity, and also that you have seen earlier that force time delta T is equivalent to the impulse. Combining these two concepts, then you have what we call impulse theorem. But as of now, look at the idea that impulse of a force or the calculation to get impulse is a product of force times the displacement. time, the displacement. Now, to see this in a much clearer figure, okay, imagine that you have one force, for example, hitting a ball by using a bat. Bola, kita nak pukul dengan bat. Alright. Now, obviously, you will find that you can't have force which is constant. Now, the idea here is the force supposed to be constant. However, when we go deeper into the story, where we plot a graph of force versus time, and we calculate the area underneath it, whereby the area is force times t, equivalent to the impulse, we find that because the time is very short, you hit people or you hit the ball in a very small time, okay, or short time, you find something here where being the average half of it, the area here is the same. And because of the concept, then when time is very short, when impact occur, contact occur, you find this idea that calculation of impulse can be used with the expression of force time delta T. Maksud dia macam ni. Bila kita tengok plotting of the graph, force varied. Kita stuck because our expression earlier, syarat dia force mesti constant. Okay, syarat dia force mesti constant, one value. However, bila kita go deeper, we find that this area and this area of force yang satu value sahaja adalah sama sahaja area dia. And therefore, we can still use the concept that impulse and change in the momentum. Look at the term closely. Change in the momentum is equivalent to one another. So our expression of this one can be translated in this version that impulse is force times t, and bear in mind we are talking about average of force or constant net force. Alright, so you have one value of force. Okay, in the case that is a vector, here it will look something like this, equivalent to the change in momentum, and brought you to this attention that bear in mind is not equivalent to this. It should be change in the momentum. So it's totally wrong to say that impulse is equivalent to the momentum, because momentum is just m kali v. So not m delta v. It should be m times delta v or delta mv. Okay, or this one. Now this theorem ataupun theory brought our attention to look at how injury occurs. Okay, and how, for instance, our figure here shows a dummy in a car, okay, brought to crash. Okay, in the case that it's crashed onto wall, perhaps we find that it brought to rest because of the airbag. Now, issues is that airbag meant to increases the time interval. When you increase the time, you find the overall force will be reduced. So overall average force reduced. That's what we want. So if you are the dummy, you are the driver, then you expect that that crash will not take away your life, hopefully. Right? And it goes the same as well in the opposite way of looking at it. If you have a smaller time interval, much shorter than this one because of without the airbag, then perhaps you will find this is the impact force getting larger, and it might be devastating to your physical. Now, let's look at our system or our example. The example is the car crash itself, whereby we are going to see the effect of force in this situation. Alright, in this example, we are going to study the use of the bumper. Is it really necessary that it crash? Okay, it just crash. Does that supposed to say that the car isn't effective? Okay, or not at a good quality? So in this car crash, we have a mass of 1,500 kilogram. It's supposed to collide, come into contact with a wall, come into contact with a wall. Crash, collides. So that's the key to indicate before and after. So the initial indicated here is towards negative direction. So you must consider the negative here. And after the collision, there is a slight backward or rebound, kita panggil rebound, in the direction opposite to original. And the whole collision is very short, whereby it's just within 0.15. So we would like to see what will happen, number one, to the product of the impulse, and number two, to the product of the force. Okay, impact, impulse, and also the force. So how do we look at it? Number one, it's always started with knowing the expression of the impulse, which in this case, change in the momentum. Change in the momentum. V final, V initial. Okay, let's look. V final occurred in the x direction. So like what I said just now, since everything occurred in the same direction, x only, one dimension, you can choose to omit the I. Boleh pilih untuk tak tunjukkan I. Okay? Kalau tidak, follow the answer script. Okay, V final here is given as positive 2.6. So, positive 2.6. On the other hand, we find the initial just now is a negative product. So, you find it's here together with the negative. Now, overall, the product of impulse is just substituting into the expression and gets the answer. Again, you can choose tak nak letak I. Boleh. Okay. But how about units? Okay. This is mass. So, kilogram. And this is velocity. So, meter per second. Alright. So, it's a straightforward unit. Kilogram, mass over second without the dot is okay. Alright. Now, what's next? Okay. Calculating the force would be getting the impulse theorem. Just now, here. Impulse momentum theorem. Combine them together, and combining this momentum change or impulse divide with the time, arriving with 1.76 to the power of 5 Newton. Alright. Now, since we are going to compare what if, okay, what if this is a case whereby it's not effective. It's not effective, whereby the car went backwards. Okay, we would like to see what if the final velocity of the car 0, means it does not rebound, yet times the same. So does the force getting smaller or larger? We find through the calculation, arriving with this force, getting consideration that V final is 0, which actually lesser. So again, okay, if you are to discuss the design of the car, especially the front boot, that destroy completely, and so that the final velocity of the car is 0, is it good or is it bad? Okay, is it good to your physical health being, or is it bad? Okay, think in terms of that.